Hello. Today let me discuss you very important topic, real gas equation or van der Waals gas equation. In this topic I will explain you how this equation is derived, what are the shortcuts and simple strategies to solve the questions connecting to real gas equation. Actually, real gas equation obtained by correcting ideal gas equation. It is obtained by correcting ideal gas equation. We have two types of corrections. One is pressure correction. You should know what is the pressure. Ideal pressure or pressure of an ideal gas is the number of collisions made by gas molecules on unit surface in unit time of a container. Suppose you have a container where gas molecules are colliding on the walls of the container. The number of collisions is considered as the pressure. In ideal gas, we imagine that there is no force of attraction between the gas molecules. But due to intermolecular force, but in real sense, in real gases, there is an intermolecular force of attraction. But due to this intermolecular forces of attraction, real pressure is less than ideal pressure. Because when there is a force of attraction, the force with which the gas molecule collide on the walls, the number of collision on the walls of the container will be decreased as compared to ideal pressure, where gas molecule believed do not experience any force of attraction. Therefore, this is very important. Pressure of ideal greater than pressure of real. Therefore, ideal pressure, pressure obtained from ideal gas equation, always greater than real pressure. Look at here. Therefore, we made this type of a arrangement. That is, P ideal is equal to P real plus P dash. What is the P dash? P dash is pressure lost. This pressure is lost due to intermolecular force of attraction. This intermolecular force of attraction attract the molecules when they go to collide on the walls of the container. This pressure loss directly proportional to two factors. One is intermolecular attraction between the gas molecule, and second is concentration of gas molecules. Look at here, when intermolecular force of attraction is strong, this amount of pressure lost is very high. When the number of gas molecule is very high, which will also decrease the pressure lost, amount of pressure loss. These two terms, intermolecular force of attraction and concentration of molecules, are directly proportional to density of gas, that is mass by volume. Mass is fixed. Therefore, pressure loss directly proportional to 1 by V into 1 by V. This 1 by V for intermolecular force of attraction, this 1 by V for concentration of gas. 1 by V represent density, where we take 1 by V. Mass is fixed, only the volume is connecting. Therefore, P dash directly proportional to 1 by V square. This proportionality constant has been removed by a term called A. Therefore, P dash is equal to A by V square for 1 mole. For n mole, P dash is equal to A into n square by V square. Why n square? Because in the case of n mole, P dash directly proportional to n by V. And this 1 by V will become also n by V, because number of moles also, when number of moles increases, these two factors also increases. Therefore, look at here, we will get like this. P ideal is equal to P real plus P lost. P lost is A n square by V square. What is A? A is the measure of intermolecular forces of attraction. Unit of A, that's a question. Unit of A. Unit of A is coming from the term P lost is equal to A n square by V square. Therefore, A is equal to P lost V square by n square. P unit ATM. V unit liter, therefore liter square. And moles. Mole is to minus 1 is 2. Okay. N is some number of mole. Therefore, mole is to minus 2. Now, let us check some values of A's of certain gases. Gas. A is the measure of intermolecular force of attraction. I said you A is a measure of intermolecular force of attraction. Therefore, gas and their values of A. Ammonia 4.17. Argon 1.37. Unit is liter square ATM, mole ratio minus 2. Sulfur dioxide 6.71. Helium very low value. Hydrogen very low value 0.024. Therefore, when A is higher, it has strong intermolecular force of attraction. Therefore, if a gas is A, if value of A of a gas is higher, its liquefaction tendency is higher. It can be easily liquefiable. It can be easily liquefiable. Remember that if value of A is higher for a gas, it can be easily liquefiable. Now we go to the next, volume correction. Ideal volume neglects actual volume of the gas molecules. And imagine that volume of container are completely available for gas molecules movement. Imagine ideal volume neglects actual volume of the gas molecules. This is an error of kinetic theory of gas. Kinetic theory says that actual volume of gas molecule is negligible as compared to total volume of container. From that kinetic theory, we get a volume, that volume is ideal volume, which neglects the actual volume of gas molecules. And imagine that volume of the container are completely available for gas molecule movement. But in reality, in real sense, a certain amount of volume blocked by the sheer presence of gas molecules. Because of gas molecules which are present in the container, certain amount of volume cannot be available for movement and unavailable for the movements. Look at here, in this container, it's a gas molecule, it's a gas molecule, it's a gas molecule. This gas molecule cannot go through this volume. It cannot go to this through these two volume. Cannot go to through this volume, cannot go to through this volume, cannot go to through this, cannot go to through this. Therefore, a certain amount of volume is blocked for this gas molecule. Suppose NP the volume blocked. Suppose NP the volume blocked by the presence of gas molecules. Suppose NP is the amount of volume blocked by the presence of gas molecules. Then V minus NP is volume available for free movement. Therefore, only the volume available for free movement is V minus NP. V is the volume of the container. NP is the volume of blocked by N moles of gas due to their presence. Where what is the B? Tell me what is the B? B is called excluded volume. B is called excluded volume or volume blocked by the presence of 1 mole of gas molecule. Excluded volume or volume blocked by the presence of 1 mole of gas molecules. Actually, B is equal to 4 times of actual volume of gas molecule. Very important. B is equal to 4 times. Many have a misunderstanding that B is equal to total sum of actual volume of gas molecule. That's wrong. It is 4 times of actual volume of gas molecule. The calculation of B is beyond the scope of our syllabus. Therefore, I am not doing that here. When I get next video, I will try to solve it. This is the gas molecule A, this is the gas molecule B. When they collide, this is the condition, the collision condition. Therefore, look at here. This volume, the volume in the dashed circle, is excluded. That is not available for the movement of a third molecule through this. This is how we calculate the B. B is equal to, I said, 4 times of actual volume of the gas molecule. 4 into, this is actual 4 by 3 pi r cube. This is the actual volume of one gas molecule into Avogadro number, 1 mole. Therefore, B is equal to, in real sense, 4 times of actual volume of 1 mole of gas molecules. What is the unit of B? Volume blocked for the moment is equal to NB. NB is the volume blocked for the moment. Therefore, B is equal to V by N. V unit liter, N mole raised to minus 1. What is this? R is the radius of the gas molecules. Now, this is how we got the real gas equation. After correcting our ideal gas equation in pressure term and volume term, you got the real gas equation. P plus AN square by V square into V minus NB is equal to nRT. For 1 mole, this is equation P plus A by V square into V minus B is equal to RT. Now, P plus A by V square is called the P ideal. This is the P ideal. This is the V ideal. RT. This is therefore V ideal from the real gas equation is V minus B. P ideal P plus A. Therefore, this P is the real pressure. What is this V? V is the container. What is B? Volume blocked by. Therefore, what is V minus B? B is the volume blocked by the sheer presence of 1 mole of gas molecule. Therefore, what is V minus B? V minus B is the volume available for the gas molecule where there is no there is no amount of actual volume of gas molecule. V minus B is the actually freely available gas molecule for movement of gas molecule. Once again, V minus B is the actual free amount of volume for the free movement of gas molecule. Now, compressibility factor. Compressibility factor tells you the deviation of, explains the deviation of real gases from ideal behavior. It is the measure of deviation of real gases from ideal behavior. It's the deviation of real gases from ideal behavior. Compressibility factor is the ratio of real volume to ideal volume. How do you get the ideal volume? Ideal volume obtained from ideal gas equation. PV is equal to RT. Therefore, V ideal is equal to RT by P. Please substitute this here. You will get a PV by RT. This V is real volume. Now, this is how we draw the graphs. Actually, compressibility factor is the function of two terms, pressure and temperature. We plot the isotherms at constant temperatures. X-axis is Z. This is Z. Sorry, y-axis is Z. X-axis is P. We plotted value of Pz with respect to P for 3 different gases: hydrogen, methane, carbon dioxide. Look at the hydrogen. It is always greater than 1 except in very low pressure. Very low pressure. In the case of very low pressure, all have Z is equal to 1. Z is equal to 1 means ideal gas or behaves as ideal gas. Therefore, every gas behaves as ideal gas at very low pressure or high temperature. Why at a high temperature? At a high temperature, it behaves as ideal behavior. That is shown here. Suppose you plot P versus Z of a gas at different temperature. Look at here. This gas. Here T1 is a greater. Therefore, when temperature increases, this plot slowly comes down and become equal to this dashed line at a particular temperature. At a particular temperature, the graph of the real gas become parallel to this dashed line. That temperature is called a boil temperature. Boil temperature is the temperature where real gas behaves ideally. Therefore, at a given temperature, at a particular high temperature, gases can behave as ideally. At low pressure also, gases can behave as ideally. Now we can go to a further explanation of the graphs. Why H2 of why is H2 always Z greater than 1? Z value of H2 always greater than 1? Why? Why? Z value of H2 always greater than 1. This is answer. In H2, A is very small. I have shown A, intermolecular force of attraction, is very small. That is, the value of A is equal to 0.024. Therefore, A by V square value can be neglected. You can neglect that A by V square. Therefore, the equation will be P into V by V. P plus A by V square. A by V square neglect is equal to RT. Therefore, PV minus PV is equal to RT. PV is equal to RT by PV. What is Z? Z is equal to PV by RT. Therefore, in this equation, we have to divide by RT here, here RT, here RT. Therefore, 1 plus PV by RT. Z is equal to 1 plus PV by RT. In this equation, you have divided by RT. Therefore, this term becomes Z. RT by RT, 1. PV by RT. Look at here. In this case, Z always greater than 1. Now, second question, why in carbon monoxide and methane shows Z less than 1 at low pressure? At low pressure. Look at here. Low pressure, there is Z less than 1. Can be 0.5, 0.7, something like that. Why this? It is happen at low pressure. At low pressure, V is higher. Therefore, V minus B equal to V. You can neglect the B term. Therefore, equation P plus A by V square into V is equal to RT. Therefore, you cross multiply, you will get like this. PV plus A by V is equal to RT. Look at the word, take that the word inside the bracket. Okay, this V inside PV divided plus A by V is equal to RT. Or PV is equal to RT minus A by V. Z is equal to PV by RT. You know Z is equal to PV by RT. Therefore, you divide by RT here, A by V RT. Therefore, Z is equal to 1 minus A by V RT. In this case, Z less than 1. Less than 1. Okay. Therefore, that value is less than 1. Low pressure, it shows less than 1. Now, last concept, why Z always greater than 1 at high pressure? Look at the graph. At a high pressure, Z is greater than 1 for every gases. Why? At a high pressure, P plus A by V square is equal to P. A by V square again neglected at high pressure. Therefore, P into V minus PRT, PV is equal to PV minus PV is equal to RT, PV minus PV is equal to RT, or PV is equal to RT plus PV. As usual, divide by RT here, divide by RT here. Therefore, Z is equal to 1 plus PV by RT. Therefore, at high pressure, you will get Z greater than 1. Thank you for watching.